Hey everybody. So one of the first things that we need to do when we're establishing our torques is a really clear diagram. And in order to start with our diagram, the first thing that we need to do is pick an axis of rotation, or I'll sometimes call this the pivot point. The pivot point. Okay. Torques will always equal to 0 if the force goes through the pivot point. There is no torque, there's no spin if the force passes through the point that you pick. So if we go along this beam here, and I want to draw the torques from each of these forces on this beam and show you what we mean. So we know that from the notes that torque is going to equal to the amount of perpendicular force to the beam times the D. And they're using a cross product in the notes, like cross R, and that's fine. That's a very university thing to do. But for what we're doing right now, I think it's going to be slightly easier just to recognize that we want the perpendicular component of the force times the distance that we are from the pivot point. This is the distance to the pivot point. To pivot. Okay, so let's look at F1. If I look at my D for F1, I'm going to call this D from here to here. I'm going to call this D1 because it's going to F1. You know, some effort on the subscripts is nice. And I'm looking at F1 here, and I just want the perpendicular component of F1. So the perpendicular component is going to be about that much here. I'll put in F1 perpendicular here. And I knew to stop right there because you always want to do a 90-degree turn. And this component here, I'll call this F1 parallel. Okay, so your perpendicular and your parallel components meet at 90-degree angles, just like your X and Y components do. If we're given the angle that the force is acting, let's say the angle, usually we're given it between the beam and the force, we're going to want to use a Z rule to bring that angle up into the triangle. And from here, we can now compute what the torque is. And I like to use a highlighter to show what the torque looks like. Just one sec. So notice how I've highlighted the actual torque. So your torque is always going to be this perpendicular force times the distance to that pivot point. It always looks like an L. The mistake that students make is they will do the force F1 times the D1, but it's only the perpendicular amount of force. And think about it, the parallel component, this force, if I were to push, like all of this parallel force would not produce any twists on this beam at all. The only force that's going to produce a twist would be this perpendicular component. And so to finish this off, I would say that the torque from 1 is going to equal to F1 perpendicular times D1. And we can now rewrite F1 perpendicular in terms of the hypotenuse. Now see how this is opposite, and we want to write it in terms of the hypotenuse. So I'm going to go one step further and say that torque 1 is going to equal to F1, and opposite and hypotenuse is a sine, theta, and then don't forget your D1. And we have our first torque. Okay, that is our first torque calculation. If I go down to F2, it's a little bit simpler here because notice F2 is entirely perpendicular there. So if I label now D2 all the way to here, okay, it's going to be a simple calculation because the L is already there. Let me grab a different color highlighter. Here's your L. That distance times the entire force because it's all perpendicular. So there's no trig involved here. I'm just going to say F2 times D2. and that torque is done. There's no trig because this is entirely perpendicular. Coming down to this last one at the end here, okay, it's F3, so then let's be really creative here and call this D3, okay. But see how it's at an angle? We have to now break it up into its perpendicular component, F3 perpendicular, and its parallel component, F3 parallel. Now the parallel component never contributes to the torque. So to be honest, I don't even label this. I'll just leave this as an unlabeled vector because it doesn't contribute to torque. It's just this distance times this amount of force. Look for the L's, okay? The L's. So to do this calculation, it's going to be torque 3 is equal to F3 perpendicular D3. I don't have an angle in there yet, so let's give ourselves an angle. Let's say we're given this angle right here, like that, and again, use your Z rule and bring it up. Okay, now we want to write F3 perpendicular in terms of the angle. So this is opposite and hypotenuse. So torque 3 is equal to F3 sine again, because opposite and hypotenuse is sine theta and D3. Okay, so these are how you compute the individual torques from the individual forces. We'll leave, you know what, F4 is actually kind of interesting as well, because what direction is F4 going to make this beam want to spin? It's going to want to spin the beam this way, and that is a clockwise spin. Notice that the forces up above, all three of them are going to want to spin the beam in a counterclockwise direction. And when we're counterclockwise, these we call counterclockwise torques. These are the positive torques. And the clockwise torques, these are negative torques. We do have an assignment for that direction there, so that's good to know. Kind of like negative angles and positive angles when you're in standard position in math class. You know, you have the positive going counterclockwise, and if your angle comes down, it's negative. That's how I used to remember it. So real quick on F4 here, it would be T4, torque 4, sorry, is going to equal to negative F4 and D4, which I don't currently have labeled, but that's okay. We'll just assume that it was there. Okay, for our very first example here with numbers, it's a fairly simplified one, and we want to find out what is the magnitude of the force of F if this is if this is kept horizontal. Here we go. So we're keeping this beam horizontal. We're lifting it up. The beam is pushing against this fulcrum here. All right. Now, what are the very first thing that I want you to do is to draw that diagram. Okay, and this one is pretty good. You could get away with drawing it on here, but I'm not gonna. There's a lot to draw. I like to do mine separate. So I'm gonna draw my beam. I'm gonna draw my beam here. All right, and we have to pick a pivot point. Without a pivot point, we can't label our D's. So the idea here, folks, is we're gonna want to pivot. Always pivot through an unknown force. Pivot through unknown force. Because any force that goes through the pivot creates a torque of 0, right? If torque is equal to F perpendicular D, if your D is 0, then your torque is 0. Okay, so it's clearly this pivot, this fulcrum is going to be putting a force onto this beam. It's probably going to be something like that. I don't know, force from the pivot. But we don't really care about this force from the pivot because it's going to go through our pivot point and it's going to create a zero torque here. So we don't really need to worry so much about that. Now, so if this is going to be our pivot, we're going to have our force down here. Here's our F. And what other forces are acting on this beam? Take a look. We have a mass of 25 kilograms. So we're going to assume that the weight is acting right down the middle. And there's our mg right there. Okay, you can start a little list off to the side if you like. Baby M is 25 kilograms. All right, and we know that the whole distance here is 2.4. So let's get that on there. I'm going to come do a little dash. This is going to be, let's call this guy D1, and I'll put my D1 to the weight here. And then I'm going to also put my second D2 right here. Okay, so my distances are always from that pivot. Now, just like what we did up here, we're going to break our angled forces up into these perpendicular and parallel components. So the first thing I'm going to do is say, oh, hey, this force is at an angle. So I'm going to break you up into your perpendicular component, F perpendicular, and your, oh, my pen is like glitching right now. Here's my F parallel. Okay. Now that 30 degrees is right here. So I'm going to use the Z rule and bring it up to here. Come on. Okay. One of the most common mistakes that people do when they first start doing it is they forget this weight. Don't forget the weight. Okay. Now, I think we're good to go. We can actually start from our first principle step that says that when we are in rotational equilibrium, the sum of all torques must sum to zero. So that means all of the clockwise torques must balance out all the counterclockwise torques. So let's take a look and find what those torques are. I'm going to have one torque from my weight. The weight's going to want to pull the beam. It's going to want to twist the beam in this, what is that, clockwise direction. And then this force going upward, it's going to want to pull the beam in this counterclockwise torque. Now the force that was coming through the pivot here, we don't care about. This torque is zero, as I already mentioned. So it's just these two torques right here that need to balance each other's off. So once you lay your first principle step out, you can then say something like this. There's a couple different ways to do it, but I think what students tend to be most successful with is saying that the clockwise torque, actually I'm going to lead with the counterclockwise torque, has to equal to all of my clockwise torques. Okay, well let's start with the counterclockwise. So it's going to be my L right there. See that yellow L? We just have to multiply those two vectors, the vector of the force times the distance. So I'm going to have F perpendicular D2. That's my yellow right there. And that's going to equal to, let's pick green. Let's do this D1 times this mg. So the green guy is going to go right there. Oops. And we're going to have mg is all down and times d1. Okay. we're almost there. We want to now break F perpendicular up into the trig. So let's see, looks like F perpendicular is opposite the 30, and opposite and hypotenuse is a sine. So then let's break this up into F I did my substitution there and did my algebra in a blink of an eye. Just my computer's been glitching. So breaking this down into F sine theta, everything else is the same. Rearranging for F by dividing out sine theta d2. And now we're going to make our substitution. Okay, making my substitution here. And writing my answer without sig figs and then with sig figs, and the answer is C. Okay, we're going to step this up now on the next example.